Hi all, welcome to new class. Today's class is the continuation of the problems related to steady state error and static error constants. So if you didn't watch the previous class, please go through it. The link will be given in the description box. So let us do the problem. The open loop transfer function of a servo system with unity feedback is g of s equal to 10 divided by s into 0.1 s plus 1. Evaluate the static error constants of the system. Obtain the steady state error of the system when subjected to an input given by the polynomial r of t is equal to a0 plus a1t plus a2 divided by 2t square. So first of all we have to find the static error constants, and static error constants are positional error constant, velocity error constant and acceleration error constant. So it is given that unity feedback system, so h of s is equal to 1. Then the loop transfer function g of s is given 10 divided by s into 0.1 s plus 1. Now positional error constant Kp is equal to limit s tends to 0 g of s h of s. H of s is 1. So we can write a limit s tends to 0 10 divided by s into 0.1 s plus 1. So while applying the limit s tends to 0, we get a 1 by 0, that is infinity. Next is velocity error constant. Velocity error constant Kv is equal to limit s tends to 0 s into g of s. So that is equal to limit s tends to 0 s into 10 divided by s into 0.1 s plus 1. So here we can cancel this s, and after applying the limit s tends to 0 we get a 10 divided by 1, and that is equal to 10. Next is acceleration error constant. So acceleration error constant Ka is equal to limit s tends to 0 s square g of s, and that is equal to limit s tends to 0 s square into 10 divided by s into 0.1 s plus 1, and 1 s we can cancel, and after applying this limit we get here 0. So it is equal to 0. So these are the static error constants. Kp is infinity, then Kv is 10 and Ka is 0. And now we have to find the steady state error. So for that r of t is given a0 plus a1t plus a2 divided by 2t square, and from this we can write r of s, that is on taking Laplace transform we get r of s equal to the Laplace transform of 1 is 1 divided by s, that is a0 by s plus for t it is 1 by s square, that is a1 divided by s square, then plus here a2 by 2 t square. So for t square it is 2 factorial divided by s cube. So we can write a2 by 2 into 2 divided by s cube. So we get a2 divided by s cube, because this 2 get cancelled. So we get a2 divided by s cube. And to find the steady state error, first of all we have to find the error signal in S domain. That is E of S equal to R of S divided by 1 plus G of S H of S, and R of S is this one, that is A0 by S plus A1 divided by S square plus A2 by S cube divided by 1 plus 10 divided by S into 0.1 S plus 1, and H of S is 1. Now here take the LCM in the denominator only, so we get A0 by S plus A1 by S square plus A2 by S cube divided by, here we get S into 0.1 S plus 1 plus 10 divided by S into 0.1 S plus 1, and we can write, taking the reciprocal, we get A0 by S plus A1 by S square plus A2 by S cube, then into S into 0.1 S plus 1 divided by, here we get S into 0.1 S plus 1 plus 10. And that is equal to, we can open this bracket here, so A0 by S into S into 0.1 S plus 1 divided by S into 0.1 S plus 1 plus 10, then plus A1 by S square into S into 0.1 S plus 1 divided by S into 0.1 S plus 1 plus 10, then A2 by S cube into S into 0.1 S plus 1 divided by S into 0.1 S plus 1 plus 10. So this is E of S, and we have to find the steady state error, and steady state error ESS equal to, steady state error ESS equal to limit t tends to infinity E of t, and that is equal to limit S tends to 0 S into E of S. So you can write ESS equal to limit S tends to 0 S into E of S. So we can apply that to this E of S. So limit S tends to 0, here we get S into A0 divided by S, then S into 0.1 S plus 1 divided by S into 0.1 S plus 1 plus 10. Then again here limit S tends to 0 S into A1 by S square into S into 0.1 S plus 1 divided by S into 0.1 S plus 1 plus 10, then plus limit S tends to 0 S into A2 by S cube into S into 0.1 S plus 1 divided by S into 0.1 S plus 1 plus 10. Now we can apply the limit. So while here we can cancel this S, and after applying the limit S tends to 0, here we get it is 0 because here there is S. So first applying limit we get is 0, then plus, here we can cancel these two S, and after applying the limit we get here 1, then here 10. So 1 divided by 10, and that is A1. A1 divided by 10, then plus, and here also these two S we can cancel, and after applying this limit we get 1 divided by 0, that is 1 by 0 is infinity, so the answer is infinity. So the steady state error for this case is infinity. Let us go for another example. Consider a unity feedback system with closed loop transfer function C of s divided by R of s equal to Ks plus B divided by S square plus As plus B. Determine the open loop transfer function G of s. Show that the steady state error with unit ramp input is given by A minus K by B. So here the closed loop transfer function is given and we have to find G of s. Also we have to find the steady state error and we have to show that it is equal to A minus K divided by B with the unit ramp input. So here C of s divided by R of s is given, that Ks plus B divided by S square plus As plus B. And we know C of s divided by R of s is equal to G of s divided by 1 plus G of s H of s, and it is given that unity feedback system, so H of s is equal to 1, so we can write G of s divided by 1 plus G of s. So this C of s divided by R of s equal to G of s by 1 plus G of s, and let it be equal to M of s. So G of s divided by 1 plus G of s is equal to M of s. Now here we can cross multiple, that is G of s by 1 plus G of s equal to M of s. Now cross multiplying, we get G of s equal to M of s plus M of s G of s. Or we can write, we have to find G of s. So G of s into, take this G of s this side, so we get 1 minus M of s equal to M of s. Then we get G of s as M of s divided by 1 minus M of s, and this M of s is C of s divided by R of s, and that is equal to Ks plus B divided by S square plus As plus B. Now we can put the value of M of s here, and that is equal to Ks plus B divided by S square plus As plus B divided by 1 minus Ks plus B divided by S square plus As plus B, and that is equal to Ks plus B divided by, while taking the LCM we get S square plus As plus B minus Ks minus B, and after solving we get Ks plus B divided by here S square, then plus S into A minus K, this B cancelled, so this is G of s. So G of s is equal to Ks plus B divided by S square plus S into A minus K. Now we have to find the steady state error, and here we can write Ks plus B divided by S into S plus A minus K. So this is type 1 system. So for type 1 system, the steady state error will be constant when unit ramp input is given, and for that we have to find the static error constant. So static error constant, which is constant, is velocity error constant. Velocity error constant kv is equal to limit s tends to 0 s into g of s h of s, and that is equal to limit s tends to 0 s into ks plus b divided by s into s plus a minus k, and after applying this limit we get this is cancelled, so we get b divided by a minus k, and the steady state error ESS equal to 1 divided by kV, and that is equal to a minus k divided by b. Hence it is proved that steady state error is equal to a minus k divided by b for unit ramp input. Next question is, a unity feedback system has the four-way transfer function g of s equal to k1 into 2s plus 1 divided by s into 5s plus 1 into 1 plus s square. Then the input r of t is equal to 1 plus 6t is applied to the systems. Determine the minimum value of k1 if the steady state error is to be less than 0.1. So we have to find the value of this k1, and the steady state error is given that it is less than 0.1. So we have r of t is equal to 1 plus 6t, then find r of s, and that is Laplace transform of r of t, and that is equal to 1 by s plus 6 by s square. Then we have e of s equal to r of s divided by 1 plus g of s h of s, and that is equal to r of s is 1 by s plus 6 by s square divided by 1 plus g of s is given that k1 into 2s plus 1 divided by s into 5s plus 1 into 1 plus s the whole square, and it is given that unity feedback system, so h of s is 1, and that is equal to 1 by s plus 6 by s square divided by, here we get s into 5s plus 1 into 1 plus s square, then plus k1 into 2s plus 1 divided by s into 5s plus 1 into 1 plus s square, 1 plus s the whole square, and that is equal to, so here we can multiply with the reciprocal, and that is equal to 1 by s plus 6 by s square into s into 5s plus 1 into 1 plus s the whole square divided by s into 5s plus 1 into 1 plus s the whole square, then plus k1 2s plus 1. Now we have steady state error ESS equal to limit t tends to infinity e of t, and that is equal to limit s tends to 0 s into e of s from the final value theorem. So we can apply the limit here. So limit s tends to 0 s into e of s. So here after opening the bracket we get s into 1 by s into s 5s plus 1 1 plus s square s the whole square divided by s into 5s plus 1 into 1 plus s the whole square plus k1 into 2s plus 1, then again plus limit s tends to 0 s into 6 by s square into s into 5s plus 1 into 1 plus s the whole square divided by s into 5s plus 1 into 1 plus s square plus k1 2s plus 1. Now we can apply the limit. So here we can cancel this s, and after applying the limit here there is s, so here we get 0, then plus here we can cancel this s, also we can cancel this s here, and after applying the limit here we get 6 into here 1 into 1, then 1 divided by here we get 1 into 1, 1 plus s whole square, 1 then plus, so here 1 plus, sorry here there is a s here, so we get here 0, then 0 plus here we get k1, so k1, and that is equal to 6 by k1, so ESS is equal to 6 by k1, and it is given that ESS is less than 0.1, so substitute the value of ESS here, that is 6 divided by k1 is less than 0.1, or we can write take this k1 here and 0.1 here, so we can write 6 by 0.1 less than k1, or we can write 60 less than k1, or k1 is greater than 60, so the value of k1 should be greater than 60. So for steady state error ESS less than 0.1, the value of k1 should be greater than 60. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.